So hi everybody, my name is Jacob Tomlinson, and I'm going to be teaching you all about GPUs in Python, which should be fun. So before I kind of get into kind of what's going on, let's talk about environments. Can you all put your hand up if you have an NVIDIA GPU in the machine in front of you? That's pretty much what I was expecting. So I've set up like a cloud environment so that you can all go and grab one and we can run through all of this together. So the way that I've done this is we're going to use Binder, but this is like a custom deployment of Binder that I set up on our GCP just to give you all a GPU per participant. So the way you're going to get there is if you head to this Git repo, which is in the Slack channel and written on the board behind me, and then if you have a look at the website link over in the corner, this is some like crazy random IP address on the internet. This is a deployment that I've just set up. So if you click that, it should take you into something that looks and feels and smells like Binder, but the only difference is you'll get a GPU as part of your session on the other side. So go ahead and click that. You'll get the spinny wheels. This may or may not take a very long time. The environment that it's going to pull is very large. That's mainly just because I didn't want to trim the environment down. So you get a big fat environment. If it crashes, if it says it failed to start the server or something, I may have got the timeouts wrong. I apologize. Binder is slightly challenging to operate. So just refresh your page. If you get stuck, if you can't get to a point where you're into Jupyter Lab, put your hand up. I've got some awesome helpers down the front here. Natty, I've lumped you in as well. But put your hand up, they'll come around, they'll talk you through this. But eventually you should get to something that looks like this. This is the first notebook that we're going to talk through in the tutorial. We're going to go through everything in Jupyter Lab. This is all just Python. I'm running this on like a workstation machine at my house, just in case I like messed up the Binder. I can still keep going. I can also show you like a couple of differences. I apologize, I've been a little bit cheap. I only gave you one GPU each, but there's a couple of things I want to show that use multi-GPU. So my machine has got two in. I can kind of demo that up here, just so you can kind of see what the rough difference is there. So what I want you to try and do is get to a point where you're in Jupyter Lab like this. You can click the plus and open up a terminal. And in that terminal, I want you to run NVIDIA-SMI. And this will print out your GPU configuration on this machine. You can see on mine, it says there's two Quadro RTX 8000s in there. Yours should say a P100, I think, is the option that I chose on GCP. If you can get to this point where you can run NVIDIA SMI and it tells you you've got a P100, that is enough for things to work, and we can go all the way through the tutorial, and that's wonderful, and I'm really happy. So what I've got down the front here, I might ask Charles to distribute these, is we're going to do the post-it note on the laptop thing so I know when you've got to different stages. So if you can, once you get to this point that you've got NVIDIA SMI and you're happy, stick a post-it note on the back of your laptop, thanks, Charles, just to let me know that you've got a happy environment and we can move forward. Please do put your hand up if you're stuck. If you need any help, we'll get you set up here because there's no point doing a GPU tutorial without any GPUs. Maybe 10 minutes? Yeah, it's not fast. This is because I just launched a whole load of VMs on GCP. They don't have the Docker image yet. Whoever hits that machine first will cause the image to be pulled. Everybody else will get put in a queue. That's why I'm going to talk at you for like half an hour about stuff. And hopefully in that time, Binder will catch up and we'll get there by the time we're actually going to need it to do some things. Yeah, another question? No, as long as there's a GPU, you're all good. This is it. Sure, I mean, this environment is like a Docker image that has everything like pre-configured. You should be all good. You could, oh, and are you going for the local setup? If you could do the local setup, Charles would be very excited to help you with the local setup. I assume there would be like 1% of folks that are going to want to do a local setup. It's great if you have a GPU. The only thing I would say is I'd be interested to know how much RAM your GPU has. In a laptop, it's probably really small. I might try and allocate more RAM than you have in this tutorial. The P100 you'll get will have 16 gig of RAM just on the GPU. My RTX 8000s have got 40 gig of RAM each. So 4 gigs. Yeah, you'll probably be fine. You might just need to tweak some numbers. If I try and make a big CuPy array that's like 12 gig or something, you'll just get an out-of-memory error. But you'll be able to see what I'm doing anyway. You should be all good. Yeah. Charles would also be really excited to talk to you about WSL. Yeah, I mean, you can do that, but also like the WSL stuff, Rapids works, all of the DAS GPU stuff, Python GPU stuff works with WSL. It's like reasonably recent, and we're kind of keen to like see it in the wild and get people going with it. It shouldn't be too difficult. Like the Windows NVIDIA drivers should get you like set up and fine. But there is in the 00 notebook, there are instructions on setting up manually if you want to. And there is a WSL blog post on there. Have a look at that, see how well you do with that. We'll see how you get on. So while you're all doing Binder and while folks are going around helping you out, let me kind of set the scene, introduce the session, give you a bit of an overview of what we're going to be doing. So I've been at NVIDIA since 2019. I am a Dask maintainer mainly. If you came to the Dask tutorial yesterday, we did a bunch of Dask stuff. My main focus is just making the GPU experience with Dask really nice. Talking about like multi-GPU, multi-node. Yep. Good question. We'll come on to Dask way later, but it's like multi-processing on steroids in Python. That's my main focus, is distributed computing. It is, and just trying to make the NVIDIA experience pleasant, right? That's kind of why I've been hired. So I don't get my hands messy with actual GPU code stuff. And I am sad about that because GPU code stuff is cool. And I'm in a really nice position where I have awesome colleagues that I can inhale knowledge from. And so I put this tutorial together as kind of a way to force myself to learn some cool stuff by coming to teach it to you. I can also then kind of be like an insider novice to you all because I've been asking the questions that you're probably going to be asking through this tutorial. There is no such thing as a stupid question. This is a weird subject. It's a super interesting one. But I'm kind of hoping that I can be this little bridge because it's very easy to speak to NVIDIA folks who are super experts on GPU stuff and they'll start talking to you about very in-depth C++ code. But the on-ramp stuff is there's a lot of space in on-ramping. So this is the intention of this tutorial. So please do ask questions. Please interrupt me. Please put your hands up. Please ask questions in the Slack channel. My nice helpers will be kind of keeping an eye on the Slack channel, maybe bubbling up questions to me if they're relevant to the whole group. So the main goal of this tutorial is I want all of you to write some Python code that is just Python code that executes on a GPU rather than a CPU. If we can get to that point, which should be the first notebook, but if we can get to that point, I'll be really happy that I've kind of taken you on that step because that was the point that I really was interested in when I joined. Was the GPU is this mysterious thing, right? It's this cool piece of hardware that I've historically bought to play video games that I know is there's cool machine learning stuff going on and whatever else people are doing with GPUs, but I don't know how to touch that. I know if I install a game and run that game, it will use the GPU. I know if I use the GPU version of TensorFlow or PyTorch instead of the CPU version, it will touch the GPU, but it's kind of just magic stuff that somebody else has abstracted away from me. And I'm kind of interested in well, how do I touch that GPU? How do I interact with this thing? And that's kind of the goal of this. Once we've gone through that of writing some low-level code, talking about GPUs, talking about how they work and what they are and what they do, we're then going to start moving up that abstraction layer to have a look at some libraries which make your life easier, fit into, hopefully, your workflows. So who here has written any NumPy code before? Cool, good. And who here has written any pandas code? Okay, so all of you will see stuff that you recognize through this talk. We're going to talk about GPU-accelerated versions of both of those. What about hands for scikit-learn? Do you do any machine learning-y stuff for scikit-learn? We will also touch on machine learning stuff on the GPU with a scikit-learn style interface as well. So as we kind of bump our way up that, and then the very last thing I'm going to touch on is how do I get more GPUs? How do I make them, making things fast with the GPU is great, but how do I go bigger and massiver and whatever? And we'll touch on that a little bit. It's a cool topic. It's kind of where I'm actively working at the moment. We're running scale tests on HPCs where we're grabbing 1,000 GPUs and getting them to do a single kind of data frame operation. I think we've got a merge benchmark for data frames that we're running on 1,000 GPU clusters to see where it breaks and falls over and stuff. So that's kind of where we're at in terms of scale. But let's dig right down to what is this weird bit of hardware. I've tried to these 4-hour sessions are long. This is your fourth one probably at this point. I'm probably not going to fill the whole 4 hours. If we can give you some time back at the end, I'm sure you won't be too sad. But I've chunked this up into 8 chapters. Each one is going to take maybe 30 minutes. Some of them have got exercises. Some of them is just me kind of talking lecture style. Some of them might be shorter than 30 minutes, right? I mean, if we get some time back, that's great. I'm also happy to hang around to the end of the session if folks want to like dive off in any particular direction. We can do off-the-cuff stuff as well. So I haven't seen a huge number of post-it notes yet, which makes me worried about my binder environment. It's still spinning. Fine, that's good. I've still got like a whole load of talking to do, but spinning is good. Yeah, go for it. That's probably one of the timeouts hitting. Yeah, that will happen. I can poke at things and see how it's doing very quickly. Okay. I have nodes, they're doing stuff. That's fine. We'll just be patient. This is I've run this tutorial. This is the third time, or maybe the fourth time I've run this tutorial now. This has worked every time so far. So let's start. Where's that tremor again? Don't know. Is it just trucks or something? Okay. It feels really bouncy on the floor. Okay, so while all your binders are spinning and the floor is shaking, we'll start working through this first notebook. Yeah. It's the heat coming out of the GPUs. Yeah. So let's talk about GPUs and what they actually are from like a hardware perspective. So when you write code, your CPU executes that code 99 times out of 100, right, when you run these things. And it's a device that you don't really give much thought to, right? You're using your computer, and your CPU is like the core of that. So when you write code, stuff happens. Sometimes you think about threads, sometimes you think about processes, sometimes you think about these other things, but they are like operating system level things that are mapping onto the processor. But these are kind of abstract concepts, even though we might think of them as quite deep down, complex things to think about. They are kind of slightly more abstracted. So we're going to like dig a little bit down into GPU land and just think about what that is. So the way I like to describe this is a GPU is basically a coprocessor. If anybody remembers coprocessors, I don't. But a GPU is basically a coprocessor, right? It's another thing in your machine that you can give algorithms to, computations to, code to, that it's just much better at doing certain things, right? It's very good at rendering pixels onto a screen, right? It's very good at doing ray tracing. It's very good at doing, it's very customized to specific things. And it is this like completely separate thing, and so we need to know how to interact with it. But we also need to know when is it going to be useful. So I grabbed this picture from the NVIDIA documentation. On the left-hand side, you've got the CPU. Right? This is a 4-core CPU, standard kind of thing. 4-core might be like low these days. I've got 12 in my laptop in front of me. I've got like 96 in my fancy workstation or servers and things, right? Like that is it's the kind of architecture where you think about running your code as like a single-threaded thing a lot of the time, right? We're talking about Python often. We're thinking about single-threaded things. Maybe you're thinking about async IO and doing some concurrency. Maybe you might start reaching into multiprocessing and doing stuff with multiple processes. But at its heart, you've got these CPU cores that the operating system is just giving code to run through, and threads are kind of being allocated. Each of those cores can do a different thing. It can do it very well. They've got certain levels of caches and stuff to kind of store things as they're going in and out. But the GPU, this big thing on the right, is very different in that it's got many, many more cores, right? Like modern high-end GPU has got thousands of CUDA cores inside it. But they're not as separate as they are in a CPU, right? They don't have the same kind of separated controls. They don't have the same kind of separated cache layers. They do have some shared caches and things, but you basically have to treat the entire device, for the most part, this is kind of getting less true now, but you have to treat the entire device as like one thing that you're going to get to do one task for you. Your CPU is really good at doing lots of different things at the same time, right? But at the moment, it's easier to think about a GPU as like, this GPU is just going to do one thing for me now, and then it's going to, probably going to do a series of things for me. But the things that it can do are extremely fast because it can do them in parallel. If you kind of set things up in a way where you give it like a big chunk of stuff and say, please do this big chunk of stuff for me in parallel, and when you're done, give me the answer back, and then we'll move on to talking about the next big chunk of stuff, right? I find that like a useful conceptual model. We do have like newer technologies where you can start slicing up GPUs and all kinds of stuff, but let's not stress too much about that. So I'm going to play a YouTube video. I don't think I'll get any sound, so I'm just going to kind of narrate it over the top here. But this is like a nice illustration of how this works. This is off their NVIDIA YouTube channel if you want to go and find it. But they managed to get the Mythbusters guys to like build a physical demo of the difference between these two pieces of hardware. So the thing, oh, don't buffer for me. Okay. The thing that he's showing at the moment, this is a CPU, this nice little robot here. It's like a little robot arm with some tracks, and it's got a paintball gun on the top. And if you ask it to paint a picture, it's going to paint one paintball at a time. It's going to do it in like a very kind of flexible way, right? This robot is quite a cool little thing. You could probably change the arm for something else. You could get it to drive somewhere else and do something else. And now they're unwrapping the GPU, right? This is still a paintball gun. It's a slightly less flexible paintball gun. It's a very much more opinionated paintball gun, but it's still a paintball gun robot thing. And every single one of these cylinders here, these are our GPU cores. And they can get those GPU cores to do kind of different stuff, but not really. Like, they're all going to do the same thing. They're all going to shoot a paintball gun at the same time. The difference is they can choose what goes in the barrel. Right? They can pick different paintballs and put those into the barrel of this paintball gun. And so if he hits his big button, he can paint the Mona Lisa, right? It's still a paintball gun. It's just a more opinionated paintball gun. And this is kind of, it's a cool video. It's a really cool video. So this is kind of what we're going to be doing in Python code, right? Instead of writing functions that execute one after another, we're going to be writing functions that execute all at the same time and do roughly the same thing. But this is maybe like, one of the concepts that took me a little while to wrap my head around is like, how different can these things be? Right? If I run all of these cores doing this operation, like, does that have to be really, really similar, like paintballs in a paintball tube, or can this be like very different? And the answer, actually, that surprised me is they can be really, really different, right? You can have an if statement that just completely forks, right, and goes off down way different branches, and each core can be doing a different thing. The limitation is they all have to be done before you can move on. So if you have one branch that takes an order of magnitude longer than the rest of the branches, your GPU is going to be very underutilized. You can have a lot of threads sat there waiting for the straggler that's doing something else. So it's very much in your benefit to make sure that all of those threads are doing roughly the same thing. And when I say roughly the same thing, I'm saying take roughly the same amount of time. So if we've got this nice device, how do we actually speak to this thing? And how do we get it to do what we want it to do? Now, again, the conceptual model that I've come to personally is to think of this device as like a separate machine altogether, but one that I'm slightly less in control of. I can't quite touch as easily. I can't quite get access to as easily. And the other kind of machine that makes me think of those things is like a server or a remote machine that I want to run something on. Right? If I have a nice server in the cloud or in a data center, how do I run code on that machine? Well, I can write some code on my laptop, and it lives on my laptop. I can have some data somewhere, and then I need to get to that other machine, right? So I would SSH to it. I would use remote desktop or VNC or something to like get a remote connection to that machine. I would then have to get my code to that machine. Maybe I'd check it into version control and check it out on the other side. I'd create a distribution and pip install it. Like, I would somehow get my code from me to that other machine. I would have to get my data from me to that other machine. And then I would have to actually say, do the thing, do the code, right? And again, that would be SSH. That would be clicking a button in a GUI app. It would be whatever it is. But I'm reaching to this other thing, moving stuff there, telling it to go. And then at the end, I have to get the stuff back again, right? Because this stuff is remote to me. And all of that is basically the same for the GPU. Right? We have to think about all of these same things. But instead of having all these protocols that we are familiar with, like SSH, remote desktop, and SCP, and FTP, and Git, and whatever, we have CUDA. And CUDA is like a heavily overloaded thing. You'll hear it come up a bunch. When I'm talking about it in the context of this talk, we're talking about doing those things. Speaking to the GPU, giving it code, giving it data, telling it to go, getting results back, asking it how it's doing today, like in terms of CPU utilization and memory utilization. So if when I said the word CUDA, you went, oh no, you said no C++. I do mean no C++, right? I know CUDA does have like a C++ language extension. That is like the historic way of doing stuff. It's a very performant way of doing things, but you don't have to do it that way anymore. This ecosystem is moving forwards, and CUDA, in the context of this talk, is just how do I speak to this thing? And we can do all of that in Python. So the main way that we're going to do that is there's a really awesome Python package called Number. You might have heard of it for like other reasons in terms of making code faster. But what Number is it's a just-in-time compiler for your Python code. So you can write Python functions. You can decorate it with Number's JIT function decorator. And then it means that next time you run that function, it will do some fancy compiling stuff. It will take your Python bytecode and put it through like the LLVM and give you some compiled output, and it will cache that. And then every time you call that function, it'll go fast. And it's really good if you're trying to optimize your Python code. But Number is this kind of, can I go from Python to compiled stuff engine? And it has a CUDA extension. So it can compile your Python code down into the like NVIDIA binary compiled code stuff that we have our own compiler called MVCC, which is like a fork of Elgin. But Number will do these things for you, and it also provides you all of these nice handles for doing the other stuff, right? Moving data there, getting data back, speaking to the GPU. It's kind of wrapped up all of this stuff to make your life easier. And so for like the big first chunk of this tutorial, we're going to be doing, it's basically a Number tutorial. We're going to be focusing on the CUDA target of Number, working through some examples. We also have other ways of doing that, right? We have a lot of people at NVIDIA that like writing C++ all day. And so they've built some really cool tools that fit into this ecosystem. And then they've exposed all of that through Python APIs and Python bindings. So all of that falls under the Rapids project, which is written on my t-shirt, which is where I and Charles and other folks around SciPy work. And a lot of these libraries are C++ implementations of popular Python tools with Python wrappers to make them look like those popular tools. So you have CuPy that looks like NumPy. You have cuDF that looks like pandas. You have cuML that looks like scikit-learn. You have cuGraph that looks like NetworkX. And then we have other stuff like cuSignal and cuSpatial and like these useful things that are kind of exposing like low-level C++ functionality up to you in Python. And we'll touch on that as we kind of go through to show you that like higher abstractions. But I really want to focus on this like lower down. Like let's write some Python functions and run them on the GPU because that's what I see as the fun bit. So how are we doing in terms of binder environments? Still spinning. Tim 3. It is an error that I see often. Sorry, I'm just Kubernetesing for a minute just to see what's going on. Right, I've done a thing. If you all refresh the page, just to give it like a chance, that might... Binder has this nice way of having these like placeholders that look like your containers you're going to ask for, and when you come in, you should like push those out of the way into like unschedulable land, and it'll give you some resource, but maybe that's not working. So let's try that and see if that's not working. Might also, yeah, I might click the link as well, because I've got 100 seats on this, or like I've got 100 GPUs on this cluster. That's like the maximum allocation I could get for this. So you're all seeing a page like this at the moment, right? And you click the show, and it is like probably saying launching server, thinking about some stuff. Okay, I'll leave this running and see if I get errors that I can debug. This big chunk here is all of you, so let's see. Well, there's a lot of terminating going on there. Maybe they'll get out of the way and it'll give you some space. what I'm going to do, I apologize. It is just a bit of a wild card setting things up this way. I do have some like fallbacks if we're like still having pain in a little while. But let's keep going and give it a bit of a chance to see if it'll come back around. So I'm going to start talking through. Oh yeah. Yeah, sure. So NVIDIA hardware, you have to go and buy. NVIDIA drivers are free, but closed and proprietary, although the like kernel modules are open now, which was an exciting surprise for those of us at NVIDIA. On top of that, you've then got CUDA, which is like this proprietary bit of the driver. And then on top of that, everything upwards from there is open source, mostly Apache licensed stuff. So Number that we're going to be looking at here is open source. It's a community project. It's not one of it's not one of ours. It's one that we just contribute to. cuDF, CuPy, cuML, all of those are open source and openly licensed. The C++ code and the Python code you'll find on our GitHub. Let me go and find that quickly. It's all on Rapids. Yeah. That's one of my backup plans. I'm sure it will. I just haven't got instructions, which might mean like hashing some stuff together, but I might ask you to come and help me do that. Yeah, so if you go to Rapids on GitHub, this is kind of our place that we put all of our stuff related to like data science, PyData, kind of ecosystem stuff. You'll find the source of everything there. So I would say, yes, this is open source, right? This is all open source stuff. It's just that it is NVIDIA only on all of these, most of these tools. I'd say all of these. If you look at Number, there is an AMD ROCm target, but the investment into that bit of code is not the same as it has been into the CUDA side of things. Yeah, so let me start digging through the first bit of this notebook, because this is going to take a little while of talking as well. There's a few concepts that I need to like set up ahead of time that I'm still not 100% confident that I've wrapped my head around. I think I'm like mostly there, but I want to try and get you at least part of the way there as we go through. So to dive into Number and how we're going to write GPU code in Number, we need to know a little bit about what does code look like when we're talking about GPUs. And you'll hear as we go through this, I'm going to use the word kernel quite a lot. You'll see it through all the documentation. You see it a lot when we talk about GPU computing. So I just want to set up a definition of the word kernel here that's relevant to this talk. I was kind of intimidated by that word for a long time. It's like, what does that mean? I don't really, like, how do I make a kernel? How do I do a thing? Is that the Linux kernel, or is this something else? Like, what are we talking about? So when I'm talking about a CUDA kernel here, a kernel that we're going to run on the GPU, I'm basically just talking about a function, right? We're writing a thing which has like a signature. It takes inputs and has outputs, and we can run it, right? It's a function. But there's a couple of caveats to running functions on a GPU, which is why we have to have this kind of extra term, because a function that runs on the GPU cannot return. It can't give you anything back from what it's doing, because this is going to be launched many thousands or millions of times in parallel, and just coordinating all of the outputs of all of those calls and putting them somewhere is like a non-trivial task. You can generate a lot of memory very quickly doing that. So that burden has to go onto the user, right? So instead of returning, you have to modify memory in place. So when we call a kernel, usually we give it some input data and we give it some output place. That's often like an empty array or something that it can populate with that data. But you just have to be a bit thoughtful about, like, how does my data go into the function? How does my data come out of the function? The other thing we have to think about with a kernel is when we call this kernel, we have to decide how many times we're going to call it. Right? This is a parallel processor. It is going to execute many times in parallel. Well, my binder just woke up, so maybe some of yours is doing things. Yeah, I'm seeing some thumbs ups and post-it notes and things. Yeah. Good. You can stand down, Richard. Thank you. Yeah, so the other thing we have to think about is how do we tell this GPU how many times to do things? And this is where we have to like have a little bit of understanding about the actual hardware and what's going on. So the way that we talk about, the way you would normally talk about, I'm going to do things lots of times, is you would say for I in range 10 million, billion, whatever, right? Or you would use NumPy, or you would do something where you are setting up some like parallel calculation, but you're deciding how many iterations of this thing there are going to be usually. Whereas instead of thinking about like an iteration, we're thinking about like a parallel execution. And we call these parallel executions threads. This is kind of a slightly overloaded term compared to other, like many other things, but we're going to be talking a lot about like CUDA threads here. A CUDA thread is just an execution of the kernel, one execution of the kernel. It's one thread. And so we have to decide, how many threads do I want? How many times do I want this function to be called? And that is like, that's related to whatever the problem is, right? If I have an array of 1 million elements, maybe I want my function to be called 1 million times because I need to do an operation on every element. Maybe I'm collapsing or doing a rolling window, right? Whatever I'm doing, I need to figure out up front how many calculations am I going to have onto my data structure. But we have like a slight constraint in that the GPU is a parallel processor, but it has a finite number of threads. It can only do a certain number of things at a time. And also, each GPU is different. As we make new ones, they have more cores in them. As we make different SKUs with different, you buy a more expensive one, it'll have more cores in, basically. And that kind of maps down onto, like, inside the chip, there are these things called streaming multiprocessors that are, like, chugging their way through these threads and doing all these executions. But the way that we chunk this up in CUDA world is we say, I'm going to have a grid of computations, right? Grid is one of these first scary words. This grid of computation is like, what is the shape and size of my calculation? Right? I've got my 1 million element array. The shape and size of my calculation is going to be 1 million executions of my thread, right? So we have this grid, but then we have to like chunk that into like some round number that we can tell the GPU about so that it doesn't matter how many cores it's got, it can kind of do it in batches so that it can get all the way through 1 million. It won't have 1 million cores, but I can ask it to do 1 million things. It might have 2,000 cores, and it will just do a bunch of batches of my threads to get all the way through to the end. So when we define our grid, we have to say, how many batches are we going to do? And batches in this context are called blocks, right? So we have threads, blocks, and grids. The grid is the overall calculation. The block has a size of a number of threads, and we have to work out how many blocks we need to get all the way through to the end of our grid. And these are silly words that I get muddled up all over the place. I apologize if I say the wrong one at the wrong time. I'm certain it won't be clear what these things mean. As we start running code, we'll kind of maybe get a bit more familiar with this. But this is like a big hurdle that took me a while to get around mentally. So please don't stress if you're feeling similar. There's a hand up. Yes. It's basically out of the scope. I think I maybe made a joke about warps in the title. But let's not worry too much about warps. This is kind of, it's stuff to do with threads can have shared cache within the GPU, and warps is like a term used in describing, these threads have got high performance cache that they can, it's like communication. It's like, yeah, it's in that category of topic, but I'm not going to touch it in this talk, mostly because I don't fully understand it. I'm going to use the word warp in a second, though, which is great. Seeing as I said I'm not going to use it, but when we decide our calculation, we have to choose these numbers, right? We have to tell it what these numbers are going to be. And so let's come up with a bit of a strategy of deciding what these numbers are going to be. So for our grid size, that's kind of the easy one, that we look at the problem and say, okay, how many times am I going to go around my for loop? How many times do I want my function to run? That is our grid size. We can decide that ourselves. But then, well, how do I split this up into blocks and threads to like make up that overall number? And if you look at the number documentation, it says the number of threads in a block should be a multiple of the warp, which is 32. But let's not worry about that. It just says it has to be a multiple of 32. And it should be somewhere between 128 and 512. On newer GPUs, it can be 1024. And it basically says, this number will depend on problem to problem, but just choose 128 and don't worry too much about it. And then as you're kind of getting into the swing of things, then you can start doing some profiling and benchmarking and seeing whether tweaking that number in different directions gets you different performance. And maybe you want to start thinking about warps and caches and like lower level stuff. But for the scope of this tutorial and for the scope of a lot of the stuff we do, choosing 128 as the block size is just like a totally safe option to do. And so we're going to do that in everything here. And the 128 is going to come up a lot. So you should all be able to like start stepping through this notebook with me if you're into the notebook environment, which is great. If you're still having trouble with getting into the environment or doing anything like that, please put your, please say something in the Slack actually, because I'm quite happy to be interrupted and answer questions. So maybe you put something in the Slack and one of these guys will help you out. But let's actually write some Python code, because I've been talking at you for like 40 minutes. And the whole point of this is to see some Python code running on the GPU. So I said at the beginning we need to write some functions for the GPU, but those functions have constraints. So what we're going to do is let's start in normal Python function land, and we'll like iterate towards being a kernel that we can run on the GPU. We'll do this in a few steps. So for me, conceptually, one of the ways I have found it useful to think about running kernels is list comprehensions. It's kind of like a nice step towards this kind of parallelism, where you're kind of giving this like parallel expression, right? You're saying, for I, foo I for I in data, right? In this first cell here, right? You're giving this kind of comprehension where you're saying, here's an iterable, please iterate all the way through it and give me the output array of that. You kind of got iterable in, iterable out. It's kind of this array world we're living in. So I've written a really simple, boring example here where we've got our function foo, and it's going to return whatever it's given. It's going to pass it straight through. I've got some input data, which is just the range 10. And I can do a list comprehension, which would just do foo I for I in data. It would just give me 0 through 9 as my output, right? I'm kind of passing a list of stuff in. I'm getting a list of stuff out. But I said we can't return, right? This function is returning. We can't do returns. We should not do that because kernels can't do that. So let's take one step in that direction. And instead of returning I, let's just put I into a list. And then that list will be the output of our function. So ahead of time, we say, here's my input data, and here's my output array that's going to store my answers. And my kernel, or what will be my kernel, is going to take in a number, and it's just going to append that into the array. And then I'm going to do my same list comprehension. A lot of things have stayed the same. And then I'm going to look at output. Right, so again, it should be the same array. We get the same thing that we got last time. But we're starting to get the structure of what it's like to write CUDA code now. You kind of set up your data structures at the beginning. You define your kernel that's going to run on them. You tell it to run on them. And then you look at the output data that came out of that and do something with it. So there is yeah, go for it. It doesn't, and it can't, and it shouldn't. And I'm just being lazy in these first couple of cells, I guess. It can't be a global. So, but we'll come on to that in a couple of cells. So one of the constraints, as well as not being a global, is that actually the GPU wants to know what the length of this array is ahead of time. I can't just create an empty array. It's the same problem as if these things could return, right? I need somewhere to put this stuff. I can't just have like an infinitely length array in GPU memory. We don't have an operating system to make our life easier here. We are like dealing with this device at a low level. So this is where NumPy can kind of come to our rescue, and we can say, well, my input data is going to be a NumPy array of these 10 elements. And my output is going to be a NumPy array of zeros. There's the same shape and size as these inputs, right? So instead of just having some bare Python stuff, we've got some NumPy stuff. But all the same, we're going to do exactly the same. Instead of appending to my list, I'm going to update the index of that list with just the value, right? I'm overloading I a little bit here. But I'm just going to take a number in. I'm going to update a specific point in the index, and then I'll get that answer back out at the end. If I run this, I didn't import NumPy. I should merge those cells. I'll do that every time I present this. So that's it, right? We are at this point now where foo here is a kernel in the definition of kernel that I gave before, right? It's taking in something, it's updating some memory, and I can use it in parallel, right? This is now like a kernel. So I can now just decorate it with number and turn it into an actual GPU kernel that's going to run on the GPU. Now, as you said with the global stuff, we can't just grab stuff from the global scope because we're running this on the GPU. The GPU doesn't know anything about our CPU memory or our global scope or anything like that. So I've changed foo here to take our input array and take our output array. And you might be wondering, like, what has happened to I in this? Each call of this function needs to know what it's doing. We're going to have this input array of elements and this output array of elements. And each call of the kernel is going to need to operate on a different element in this context. So each kernel needs to know what to do. And this again was like another step forward in like knowledge for me, was the fact that each thread, as executing on the GPU, can speak to the GPU and say, which thread am I? Within my big grid of 1 million threads, who am I? And it will give it an index within that grid. So that is how we can allow our threads to go off on different paths and branch and do whatever, is because they each have a discrete index that is assigned by the GPU as things are running. And the way that we do that through the NumPy, the number API, is we use this cuda.grid method. So basically just saying here, what is my one-dimensional index within the CUDA grid? So we're saying 1 here. I kind of wish you could just omit this and it would give you the one-dimensional one, because we'll introduce that properly in a bit. But we're kind of saying, what is my index within the grid? And because I'm deciding I have an input array of 10, I have an output array of 10, and I'm going to run this thing 10 times, those like indexes map along. I'm just going to say, take index 0 from here and put it to index 0 there. Oh, I'm number 4, I'm going to take 4 and I'm going to put it to 4 over there. Right? It's just going to do whatever its index says it's going to do. So this now is actually a GPU CUDA kernel. This is just a decorated version of our kernel before. It takes our input array and output array as arguments, and it asks the GPU what its index is as it's executing. And so it can do the appropriate assignment. So the last thing we need to do is actually say to the GPU, please run this thing for us. And because we need to decide what our grid size is ahead of time, we said it was going to be 10, right? In this example, our 10 element thing, we're going to have a grid size of 10. The way that we configure this in Number is on our function that is decorated with cuda.jit, we use square brackets, right, to give it the block size and number of blocks. So here we have block size first. No, we have number of blocks first. We have 1 block with 10 threads in it. We're just doing the length of the data. So we're kind of configuring our kernel at this point. We have this kernel that can do stuff, but we're going to say to it, right, you need to run this number of times. You could assign the square brackety bit to another variable if you wanted to keep track of a specific shape of that kernel. But often it's common to do, start my function, use some square brackets to tell it how many times to run. This is my for loop, basically. And then we give it the arguments like a normal function call. So we'll see a bunch of weird function calls like this. As we go, you'll get used to them over time. And if I run this now, I haven't imported CUDA. Really should merge those. I get a couple of warnings, and then I get an output array. And this is like the earth-shattering, exciting moment, because this function executed on the GPU rather than on the CPU. These lines of code in here were GPU instructions that happened on the GPU. And it's really nice to be able to just look at Python and see that being able to run on the GPU kind of in a low level. And for me, this was like, oh yeah, I've done it. I've written some GPU code. I kind of understand, but not really. Now, there's a couple of warnings here that's kind of basically saying like, that was a very small problem. The GPU is not really for you. And that's fine, because these are just toy examples. The other warning is about data, which we'll talk about in a second. So unpack that. Now, let's scale this up a little bit. Instead of working on 10 elements, let's do 30 million elements. It'll probably still tell me this problem is too small. But let's make a big NumPy random array with 30 million random elements in it. Let's make ourselves a big output array full of zeros for our results to go into. And we're just going to double everything in our input array. So we've got a kernel here. This is our doubling kernel. It's going to, in Python, sorry, I'm going to start in Python, and then we're going to move to the GPU. So if I was going to double everything in my NumPy array in the most inefficient, unpleasant, pure Python way possible, this is how I would do it, right? I would have Python loop over my array and update each element with the double of the input. And if I run this, I think on my machine it'll take 10 seconds or so. But let's let Python chug its way through this big array and do its thing. Okay, 12 seconds, basically. But that's kind of how I would do things in like a really noddy way. Now let's move over to the GPU and think about how we can parallelize that algorithm, because this is like an embarrassingly parallel thing. We're just taking an item, doubling it, putting it somewhere else. We can parallelize this in a really like trivial way. So we've still got our input array, so I'll leave that alone. I'm just kind of resetting the output array here back to zeros. I'm doing a little bit of maths to work out my blocks and threads. Right? Instead of me deciding I'm going to have one block of 10 threads, I'm just going to say, well, my block size is 128, and I'm just going to calculate how many blocks I need to get all the way through my number. So to get through my 30 million items, this shape here, I'm just going to divide that by the number of threads and calculate the ceiling or whatever, and I'll get my number of blocks to work my way through. And we'll do this calculation a lot, right? It's just work out how many blocks do I need to get all the way through. I then have a CUDA kernel here, which is going to take our input array and our output array. It's going to get its index to say which item in the array do I work on, and then it's going to update the output with the double of the input. And then I'm going to do my strange GPU call, where I give it the number of blocks and the number of threads in each block. I'm going to give it my input and output. And that's going to run on the GPU in 191 milliseconds, right, compared to the 12 seconds that that took in pure Python. This has stopped telling me that this is a small problem, which is helpful. It's still telling me you're not doing very clever data stuff, but that's fine. It's just preempting my next bit. But like at the beginning of this talk, I asked you to put your hands up if you used NumPy before, so I'm sure you're all screaming in your heads like, why are you doing a for loop in Python? Like NumPy is amazing and wonderful. Why don't you just use NumPy? And of course we can just use NumPy, right? We can just do our array times 2, and NumPy will do this on the CPU. And like the workstation I'm on has got 96 CPU cores, so NumPy is very nice on this machine. If I time how long this takes in NumPy, oh, I'm surprised. Shouldn't have done that. This normally like is, there we go, 50, yeah, oh, okay. Maybe that was just an internet lag. Right, it's come back in 56 milliseconds, right? So that's come back in a third of the time, nearly a quarter of the time that my noddy GPU calculation took. So badly written GPU code is still not necessarily better than well-written CPU code, right? We have to really think about these problems and dig down. But one of the reasons why we're paying so much pain here on the GPU, one of the reasons why I would consider this to be badly written, enough that it's giving me a warning, is when I called my kernel, I gave it random array and output. These are NumPy arrays. These are in memory on the CPU. The GPU knows nothing about these. And this is where number is really nice, but also can trip you up a little bit, is I've given it a CPU array, and it's gone, oh, you don't mean that. I'm going to copy that onto the GPU. Then I'll do the thing, and then I'll copy it back for you. And then you don't have to worry too much about that. But that you pay a penalty for that, right? Like it takes time to move data from the CPU to the GPU in the way it takes time to like SCP data across to a server or something, right? There's a transfer time that you have to pay. And the kernel that we're running here is a very, very small, very, very simple kernel. And so the amount of data we're moving compared to the performance of the function is just not stacking up. So we're actually paying a lot of pain. But we don't have to let number do this for us. We can be more explicit about our memory. So let's be explicit. Let's take our NumPy arrays, and we'll use the calls cuda.toDevice to say, cuda, can you move, number, can you move these to the GPU for me now at this point? So if I run these, we'll get these GPU random array and GPU output. And if I just have a look at one of those, you can see this is no longer a NumPy array. This is now a weird cuda device array that's sitting on my device. This array has moved into the RAM of the GPU, and I've just got this pointer to it now. But I can give that pointer to my kernel and let the kernel operate. So number's not going to do that transfer, and it's not going to do that transfer back. So if I now time this running on there, it's now taken 12 milliseconds. Right? So this is faster than the CPU operation if we remove the data transfer from the equation. But the data transfer is in the equation. You've had to pay it at the point that we moved it. We also need to realize that our answer is on the GPU still. Right? The output is still at arm's reach, and we now need to get that back. So we also need to use copy to host to say, can I have my array back? And that pops out as a NumPy. Yeah, NumPy. Get all these words all over the place. That pops out as a NumPy array back on this end. But that cost time, that was kind of an expensive operation. And the time where these are, like, that you would use this, that would be really useful, is when you're going to move some data to the GPU, and then you're going to do stuff to it, and then you're going to do something else to it, and you're going to do something else to it. You're going to make lots of Python calls, and you're going to keep operating on that data, and then finally, at the end, you're going to get it back. Hopefully, in most of the situations, thinking about if you're doing some, I don't know, weather data stuff, you're going to move your data to the GPU, you're going to do a whole bunch of stuff, you're going to do a whole bunch of stuff, and then hopefully the thing that comes back is a plot that you can look at, right? You don't want anything else back. You just want the kind of final result, which should be smaller. Of course, that's not always the case, but this kind of illustrates here. If I just used NumPy arrays here and had 3 kernels, foo, bar, and baz, if I called each one of my NumPy arrays, number would copy the data down, run the kernel, and pass it back, and then it would, for the next one, copy the data down and pass it back, and it would just keep thrashing that data back and forth in like an inefficient way. So we would just set this up with, okay, here's my data, put it on the GPU, I'm going to call each of my kernels, and then I'm going to get my answer back at the end. This is where kind of manual memory management is going to be beneficial. So that's the end of this first notebook. been going for a good long time, so thank you for bearing with me, especially with the Binder startup. Now we've got a number lab here. What I'm kind of aiming to do is I'm going to talk at you for a bit, not as long as this, because I've done like the intro plus some Binder stuff plus the first notebook. But we're going to do like a notebook and then a lab, and then or a notebook and then a break or something like that. The last ones have not got labs, but let's work through this. I'm going to ask you to kind of apply the things that we've just talked about in that notebook. We'll maybe take a 15-minute break at this point. But if you take all of your Post-it notes off, because we're going to start the exercise, and then start working your way through this, and then when you're done or bored or want to move on, stick your Post-it note back on. Also feel free to take a rest break and go get a drink or whatever from outside. But I'll aim to resume at about 22. Forwards, work through the lab solution, and then we'll move on to the next notebooks. So in this lab, it was just asking you to do FizzBuzz, basically, right? So standard computer science thing. But we're going to take all the numbers in the range of 50 million, and we're just going to calculate which ones are FizzBuzz and FizzBuzz. So we're going to start off by importing our NumPy and number, our CuDF from number, and we're going to make our array. We'll make this with NumPy. So we'll make our 1 through 50 million with NumPy with a range. And we need to create our output as well for our data to go into. So let's do zeros like that. So we got our big zeroed out array. And then we need to calculate the size of our grid, right? These are always like the steps you take. Is like, what does my input data look like? What does my output data look like? And what does my calculation look like? And you need to decide those three things. So we've got 50 million elements, and we want to do an operation on each one of those. So our output is going to be 50 million, and our calculation is going to be 50 million. So we just need to calculate that, basically. We're going to do the same thing we did before. We'll choose our arbitrary thread size of 128, because that's a safe number to choose. And we'll just divide the shape of our array by that size and take the ceiling to work out how many blocks we're going to need. Now, you might notice in a lot of these situations, I've been calculating the number of blocks that I need, but I've been calling ceiling on that. So the number of blocks that I have will be a multiple of 128, but that might extend over the end of our array, right? We might go off the end of our 50 million. That's not ideal, and we will kind of counter that later, but it's also not the end of the world. Those threads may just operate on indexes that don't exist. They will actually overflow. They'll just read random bits of RAM and write random bits of RAM, and that is not good. So we should handle that later. But given that we're only going to go off the end by a little bit, and we're the only ones doing anything on this GPU, it's not like a killer situation. But we should guard against that later. Now, here's our FizzBuzz algorithm. Now, we're using NumPy arrays here, so we can't actually put fizz and buzz and FizzBuzz in here. So we're just going to substitute the numbers 1, 2, and 3 for FizzBuzz and FizzBuzz, and we're going to leave the rest as zeros, right? So we're just going to have a big array of zeros with some 1s, 2s, and 3s kind of littered through to represent where we found the FizzBuzz and FizzBuzz. It's going to be basically a mask. So when we call our function, we're going to say, who am I? What is my thread index? Which element do I need to operate on in this large array? I realized I was like partway through typing an answer from Slack, sorry, to like completely jump over. Somebody noticed a mistake in one of these where I wasn't updating the right thing in the right place. I appreciate like spotting typos in this. I can go through and fix those up. So if you do spot any more mistakes in this stuff, please shout. So I'm gonna take my number out of my input array just to make it a bit easier to read the code. And I'm gonna say, is it a fizz, is it a buzz, or is it a FizzBuzz? And if it is, I'm going to update its location in the output array to basically make this mask, right? And then I'm going to time how long that takes to run. So on our 50 million elements, we just have a look at the first 12. That took half a second to go through that array and update it. And you can see, you've got 0, 0, fizz, buzz, 0, fizz, etc., etc. There was also like a extra credit to just say what was the highest number of fizz. We are still in NumPy land, so you could just do this in NumPy. You could just do np.where to work out, oh, the highest fizz in here was for 49,999,998. So let's move on away from kind of abstract, strange things. and talk about like slightly more tangible data structures rather than just playing around with arrays of numbers. We're still going to play with arrays of numbers, but we're just going to have some meaning to those. So let's take an array of numbers that we deal with all the time, an image, a bitmap, and do some stuff with that. So we're going to use matplotlib because matplotlib will very nicely read in an image and give us a NumPy array of that structure. And then we're going to play around with that NumPy array on the GPU. So let me just import matplotlib and a few other bits and pieces, set matplotlib up. And because we're talking about number, we're going to read in the number logo, which is stored in here. If we have a look at the type of this that matplotlib's read in, this is a NumPy array. It's just a NumPy array. It's nothing kind of fancy. If we do imshow matplotlib, I know we get our axes and things, but you can just see this is the number logo stored in an array. And in order to operate on this, let's move this image onto the GPU so that we can start messing with it in place. So we're going to use cuda.toDevice to push our image onto the device. And we're also going to create some zeros, the same shape and size as our image, and we'll push that onto the GPU. I could actually also just ask number, can you make some zeros directly on the GPU, this shape and size? Or we could, it's slightly more efficient than doing this, but I like this conceptually of saying, here's our output, we put it on the GPU. Now, this array is not the one-dimensional index that we've been playing with. The one-dimensional array we've been playing with this whole time. This has got like a more interesting shape to it. If we have a look at the shape of our NumPy array, it is 116 high, 434 wide, and 4 deep. If we think about it as an image, right? It has an X and a Y of pixels, and the depth here is red, green, blue, alpha. And it's just a value of red, green, blue, and alpha, basically, within a grid. So when we work on our image, we kind of want our calculation to be that same shape and size, right? We want to be working on, depending on what we're going to do, we want it to be the same shape and size. And what we're going to do in this notebook, but I think in this notebook, in this notebook, what we're going to do is we're going to blur the image. Blurring the image is like a nice little thing. And we're going to do that in order to calculate a blur. We want to take each pixel, look at all of its neighbors, and calculate like the mean of all of those pixels, and then update the output with the mean of its neighbors, basically. Right? So we're just going to do a mean of all the neighbors for every single value. And we only want to be blurring kind of across. We don't want to be blurring across the color channels. We just want to be like blurring the image itself. So we're going to be operating on red independently to blue, independently to green. We won't worry about alpha. So in order to do that, let's think about our calculation also as a three-dimensional structure. Right? We have our X, Y, and channel, and we're going to think about our calculation as having X, Y, and channel. So we have to decide what our number of threads per block are up front, like we had to do before. But we're now working in this fancy three-dimensional indexing world. And so we need to specify our threads per block in 3 dimensions. So what numbers do we choose? Well, like I said, the documentation says choose 128 because 128 is a safe number, so we're definitely going to choose 128. But I'm doing this in 3 dimensions, so I need to choose 3 numbers that multiply together to make 128. So here I've chosen 2, 16, and 4. And the very arbitrary reasons for why I chose those numbers is because there's 4 color channels. So I chose 4 as the last number. Our grid is going to be kind of 1 block deep on the array, right? I then chose 2 and 16 because that's roughly the aspect ratio of the image. It doesn't hugely matter. That could be a square. That could be whatever. But I've just kind of chose those numbers arbitrarily and made sure that they multiplied up to 128. So we have this kind of magic number put in here, this threads per block. And now we need to calculate, well, how many of those blocks would I need to pass over my image in order to modify every single pixel? So I'm going to calculate my blocks for each of those axes. So there's a bit of unpleasantness here, but we end up with the blocks per grid. And I should print this out at the end, really. Okay, so it's going to take 58 blocks on the Y dimension, 28 blocks on the X dimension, and 1 block deep. We don't really need to care about these numbers now. We've calculated them. This is going to make sure we've got full coverage of our image. We can make sure we can see what the overall size of this calculation is going to be, what the size of this grid is. If we just multiply all these things back together again, we can see that our calculation is going to be 116 by 448 by 4, which 116 lines up. It was 448, so it's slightly over on the Y dimension. and then it's the same on the Z dimension, I guess. So we've got this kind of stencil that's going to fit over our image, and there's like a whole bunch of like stenciling stuff in Number to make your life much easier doing this kind of thing. But I wanted to do this from like the low level to show you what we're doing. But you can see we've kind of made this big calculation thing that we're going to sit on top of our image, and it's going to do some operation to it. So let's write our kernel now. So for each thread, we're going to work out where we are in the image. And the GPU supports multi-dimensional indexing. We've set ourselves up with three-dimensional shapes for our calculation. So we can ask for our index in 3 dimensions as well. So instead of doing cuda.grid of 1, we can do cuda.grid of 3 and say, can you give me basically my X, Y, and Z, or X, Y, and C position within this image for who I need to operate on. So each invocation of this will get X, Y, and C. And then I'm going to do my safeguarding that I talked about before. We're just going to check, am I over the bounds of this image or not? Am I outside of the shape? If I am outside of the shape, the else is just going to, the invocation is going to finish, right? We are going to launch some unnecessary threads here. But those threads are going to just return. They're just not going to do anything, and that's fine. We only care about threads that are kind of wandering off doing long things. It doesn't matter if they any kind of short circuit and finish early. So anything that's inside the image is going to update the output position with the mean of the input position with its neighbors, right? So we've just kind of got that. I'm going to break it down here so it's a little bit visual, but you can see we're just taking all of those values, dividing them by 9 after they've added them together and updating that. So we're calculating this blur. And then for running our kernel, we can do this on our image, but this isn't a very deep or very aggressive blur, right? We're just going to take the mean of all the pixels. We'll get like a mild blur. But what if we want to blur it a lot? Or we could call this multiple times. And this is one of those situations where we can do this blur in parallel, but in order to do the second blur, we need all of the updated values of that kind of intermediate step. So this is where we're kind of doing a bunch of parallel operations sequentially to build up the overall thing that we're trying to solve. So we're going to just, in Python, do a for loop, right? Something that is well known to be slow. We can just loop over this. We're doing a lot of very fast things just inside the loop here. So we'll call our blur function to blur our image, and then I'm just flipping the pointers over, right? So the output becomes the input becomes the output. So we're just going to take our image and we're going to blur it to here. Then we're going to blur that back into the array that we had, and then we'll blur it some more into that one. I'm just going to kind of flip back and forth, reusing the same memory over and over just for efficiency, rather than having a load of random intermediate arrays hanging out. So if I run this, I think I should probably have, I haven't actually run my code. There we go. Run that, run that. I think I need one more flip, actually. I think it stays in like a flipped position. But if we now have our GPU output, which is our blurred image, and if we just pull that back onto the CPU with copy to host, we can do matplotlib imshow again and see our nice blurry number. Oh, you mean as in it would go off out of the bounds? So at the moment, around the bounds, it's just reading noise. I haven't done this in like a super intelligent way. Right? So you might want to put that inside your kernel of like, oh, if you are 0, maybe you only want to be reading the positions within the image. It's still reading -1, which is just kind of off the array into RAM noise land. It's an overflow. Yeah, it doesn't throw an error, and you can see there's some like weird darkness around the bounds of the image where the noise is just kind of coming in and making it a bit blurry across all the channels. Yeah, exactly. So this is what I was saying at the beginning about this is like a much lower level thing of like you're operating with this device. You don't have an operating system to kind of help you here, which is kind of where like NumPy and the operating system are like working together to make sure you're managing memory nicely. In this, you have access to the RAM, and you can do bad things as well as good things. There are, yeah, exactly. It's definitely got that vibe to it. There are other things to help you out. We have other packages like RMM, which is like the rapid memory manager that helps you do slightly more intelligent paging and things. But this is that kind of lower level of dealing with memory. So we're kind of quickly back to the next lab. So I'm going to give you another 15 minutes to do this. I'd forgotten how short that notebook was actually. But I'm going to ask you to run through basically the same thing, but this time I'm going to ask you to do a grayscale, basically make this image black and white. So instead of blurring, when we're doing this grayscale, we're taking the mean of each of the channels, right? We've got red, green, and blue. We're taking a mean. So this is actually a two-dimensional calculation rather than the three-dimensional calculation we did before. We only care about the x and y value, and then each of our kernels is going to operate on red, green, and blue and update red, green, and blue. So this is basically the same as the blur one, but this is two-dimensional instead of three-dimensional. So give that a go. Please put your hand up if you need some help. Also, again, rest break if you need a rest break. Email if you need an email. Yeah, question? Our input and output are both three-dimensional, but the calculation is two-dimensional. Yep. Right, I'm going to take it. Right, okay, I'm going to get going again. My Jupyter just died. But let's work through the solutions to this next lab, and then we'll move on to something else. So I think we were here in the grayscaling one. So this is pretty similar to the first one, right? We're going to import matplotlib and kind of get ourselves set up with dependencies and things. We'll import our number image and just make sure we've got our logo here, and then we'll push it down onto the GPU. Once it's there, we'll work out the size and shape of our calculation. So as I said, this is a two-dimensional calculation because we need to read all the channels in. So it still has to be a multiple of 100. Still has to be a block of 128. So we're going to choose 16 and 16 to multiply up to our 128. And then we're going to calculate how many blocks we need to do that. So it's pretty similar to the last one. This is just 2 dimensions rather than the 1 and the 3 that we've seen already. Then our function here, we're going to get our x and y position. Where am I in the shape of my calculation? And this is only 2-dimensional this time. And again, we're going to do our boundary check here. I was just chatting to somebody during the thing about like these boundary checks work both ways as well, because before we were like writing off the end of the array, you can also read in from off the end of the array, and it doesn't warn you about these things. So you have to like be conscious of making sure you're doing boundary checks when you write your kernels. We're then going to take the average across the 3 RGB channels. We're not going to include alpha in this, just RGB, and that's going to give you your average, right? It's going to put us on this gradient from black to white. And then we're going to update our output array, but we're going to update R, G, and B with the mean. Each one will make it the same. So this is kind of why we've got these two 3-dimensional things, and we've got a 2-dimensional calculation. They're going to be reading in 3 values, writing out 3 values across those dimensions. So if we run this, then we only need to do this once because we only need to make it black and white once. And then if we pull it back, we can see it goes gray. So this is how we can do all sorts of different like image processing things. We can work on these large arrays. Hopefully, you can kind of see how we can use the GPU for these kind of operations that are parallel, right? Each operation we did on each of these pixels was kind of independent of anything else around it. Sometimes it's not always fully independent, like in the blurring. We had to wait for each step to completely checkpoint before we could move on to the next one. So we can do that kind of in Python, calling down into the GPU, and really do like a mix and match here to get the best. Now, to move on to like a slightly different topic before we jump into higher level libraries. So far in these notebooks, in one of the earlier notebooks, I said to you like, oh, this is really exciting. We got to this point, we wrote this function, we ran it on the GPU, and isn't that exciting we got here? And you all very kindly trusted me that it had run on the GPU, right? Because it looked just like something else. You just called a Python function and it ran on the GPU. How do you actually be sure that it ran on the GPU? How do you know what's going on? So let's like go off on like a slight little detour into, I'm not going to go as far as like debugging because you have to start pulling out like NVIDIA toolkits and stuff for really getting deep down, but let's have a look at like observability of the GPU. So at the beginning, I asked you to run NVIDIA SMI to have a look at what was going on your GPU, mainly just to make sure you had one and that it was there and that we could see it and that your drivers were installed and things. Running it again now, we can see I've got like a few things in my list. If you ran this, it might be a bit longer because I've just restarted my notebook because things died. But I can see I've got a Python process here listed down in the list of processes now. They're saying, oh, this Python process has been speaking to the GPU. It's been doing stuff on the GPU, and it's allocated 163 megabytes of memory on the GPU. So that's like one way we can look and see, okay, my Python process is actually talking to the GPU. We can also kind of get information here about how much memory is being used, how much memory we have altogether. You know, this GPU has got 48 gig of RAM or whatever. Yours will have 16, I think, on the ones I chose on Google Cloud. It also just tells you about power outputs and temperatures and all that kind of thing. This is kind of just like a useful overview of stuff. But what about actually like utilization? How much memory am I using as a percent is here, but what about how much am I pushing it? There's a 0% listed here. And it says, okay, these GPUs are doing nothing at the moment. They are idle, they're not busy. But we don't want to be running NVIDIA SMI over and over. You could do watch NVIDIA SMI or something and get like a periodic table that is going to be updating. But we have other tools that can help you reach into this. If you've had a peek over on the left-hand side, there might be a little icon that you don't recognize in JupyterLab. If you're a JupyterLab user, there's like a tiny little picture of a GPU on the side. This is because in this environment, we have the NV dashboard extension installed. If I just search NV dashboard, this is both a standalone dashboard for your GPU and also a JupyterLab extension. You can install it and do both. You can run, it's very slow. You can run NV dashboard from the command line, and it will just start like a little web server. It's kind of inspired by the Dash dashboard if you've used that. You can view it in a web browser, but also it has this nice JupyterLab extension where you can pull the plots out. So I want to see, okay, how busy are my GPUs? Let's grab that plot. I'm going to smush it over here. How much memory am I using? Let's grab that plot, smush it over here. I can now see some utilization of my hardware. I can also get, we can get overall machine resources like CPU and other bits and pieces. If you've got multiple GPUs that are connected via NVLink, which is like the modern successor to SLI if you're into gaming from a while ago, the GPUs can talk directly to each other via a little clip that you put on the top. We can see the throughput through that network as well. So now if I go back to my notebook, and if I do my black and white again, it starts so fast, okay. Sometimes when I'm doing things, these graphs show stuff, but I think this is such like a minimal application that, yeah, the GPU just does that fast. Let's try doing, maybe the blur one is a bit heavier. Oh, did you see it flicker? Did anybody see it flicker? I'll run it again, just to see if it does it again. Let's do it that time. Run all cells. Oh, it's just sad. What did I do? No, I just, yeah, there's like a thing. Okay, there was a flicker. Some of you saw it. That was actually my CUDA context initializing, which is a slight red herring, but it means I can actually come and do it in other notebooks as well, and you might see that flicker. Yeah, there it was, right? The GPU is not busy in any of the things that I'm showing you. We might make it busy later, but you can see here now, I'm going to run some code and my GPU is busy. This is kind of like opening Task Manager or Activity Monitor or whatever your preferred thing is to see inside your machine. Windows is quite good at showing you what the GPU is doing. Linux is less so. These are useful tools for finding out what's going on. So this next notebook is going to kind of dig a little bit into how this works. If you have a look, there is a little GIF on here. This is on like it's quite small, isn't it? I'll get a bit bigger. You can see there's like an animated screenshot thing. This is on a server that's got 8 GPUs in. You can see a utilization bar for each of those GPUs, and it's running through. This is running through a big dash graph, and each GPU is busy doing stuff. But hopefully you get the idea that at the top you've got GPU utilization that I've put up here. They're doing stuff. They're still not hugely taxed in this workload. The memory is below that. And then below that, we've got the memory throughput between them. So these GPUs have got like little NVLink connections to each other, and they are handing data back and forth between them. And you can see that going on as well. So within this environment, it's quite a nice way to see what's happening. But if you don't have that, I'm not sure if we have the proxy set up properly actually, but you can, if you run NV dashboard and go to like port 8000, all of these plots are just like on a page, and you can click through some tabs and view those plots. Question? Yeah, you can just always have this open if you want to see what's going on. Now the way that this works is we have something that's this is part of the driver actually. If you look at the NVIDIA SMI output, I thought I mentioned it in here. Okay, maybe ignore me. Anyway, we have this PyMVML, right, which is the NVIDIA markup language, right? This is the Python interface into the NVIDIA way, and it's basically just a way of querying the GPU and saying, "Tell me about yourself." So if we can do this manually in Python, and we'll just kind of dig into that for a minute, so you can see if you ever want to build your own things or maybe print out some information about the machine that you're on in a Python script. PyMVML is like a really useful way of just getting stats about the hardware you're on. I see it used a lot in like the HPC community. If you're going to submit onto a node, maybe you just want to print out the make and model and RAM and all that kind of stuff of the node you get allocated on or something. So if we import PyMVML, we have to initialize it. This just kind of sets us up to be able to communicate with it. And then we've got all these calls, like we can do device get count, tells me on my workstation I have 2 GPUs. I can say what's my driver version. And then I can grab some handles, right? So the way that this works in NVML is you get like a handle to a device. This is like an object that represents the device, and then you can use that handle to ask that device things about itself. So I'm going to loop over the number of devices I have. I have 2, and I'm going to get a handle for each of those devices by its index. You see that our devices get indexed. I've got GPU 0 and GPU 1. Everything we've done so far just selects GPU 0 to do whatever it's doing. We will come on to like more about stuff in a bit with multiple GPUs, but everything's just happening on GPU 0 at the moment. You've all only got GPU 0 on the environment set up. If I grab that, we get these couple of handles. This is just mapping onto C. You can kind of see this, so we're going to see it. But then we can do things. We can say, get device name for my GPU. So let's loop over all of our GPUs and just get our device name and have a look at those. So we can see, oh, these are Quadro RTX 8000s, like NVIDIA SMI told me that they were. I can also say, can I have your memory info and see how much memory is used for all of my GPUs? I can say, oh, I'm using 1 gig and nothing, basically. Like I said, everything's happening on 1 GPU. And I can see how much is free. These are rounded numbers, but you can kind of see I can query into my device. I can find that information. And this is what we've used to build these dashboards, basically. These dashboards are just written in Python. You can kind of hack about with them and play about with them and get stats for yourself. So before we move on, there's like a few other tools as well. There's NVTop, which exists, which I won't go through the effort of installing it in this environment, but NVTop kind of gives you top style view onto your GPUs. You can see utilization as graphs. You kind of get the processes as well, a bit like NVIDIA SMI. Glances also has, I don't know if there's going to be any pictures, but Glances is like a utility monitor on Unix systems. I use it quite a bunch on my laptop, and it will show you kind of utilization of your GPU as well. Right? So there's a bunch of tools out there already that just allow you to see your machine, but they're just not necessarily in the places you would expect to find them. So these are a few places you can go to find those things. Now, the other thing I want to show you before we dip back into some code of actually doing things is to talk about, we've talked a bit about number. And at the beginning, I briefly mentioned PyTorch is a thing and TensorFlow is a thing, and they have GPU support. We're also now going to go on and talk about some other libraries like CuPy and cuDF. These are all GPU libraries as well. And when you're doing a piece of work, it's very unlikely that you're going to be using one tool. You're most likely going to want to use multiple tools. So let's look a bit about how things play together. As we've seen, memory exists on your CPU, you move it down to the GPU, you do stuff to it. These arrays that we've been moving around are just arrays of data, right? In its simplest computer sciencey form. And they've got fancy clothes on, right? They look like this NumPy array. They look like this number CUDA device array or whatever. But they are just like an array wrapped in some Python stuff so that we know what to do with it in our code. But one of the big efforts that we've kind of pushed on within the Rapids community and kind of broadly over GPU, data sciencey, PyData stuff is let's make everything play nicely together. And let's try and avoid any copying of memory wherever we can avoid it. Because that's the big pain that we see all the time, right? We've seen CPU to GPU memory copying. But what if when I want to switch from one tool to another, do I have to like copy my array from one tool to another? Like that's going to end up like exploding how much memory I'm using on my GPU. And I've got this like transient state. I don't want to do that. So in order to deal with this, we have kind of two protocols really that have kind of come out of the community for doing handoff between one library and another. So you have DLPack, which has been around for a long time, which is kind of allows you to convert your array into this kind of intermediate representation of the array on the device with a bit of metadata about what it is and how big it is and where it lives in terms of memory addresses. And then that can be like sucked into something else that can read in DLPack. So you can basically hand one array to another library via the, you can do, a lot of libraries have like a to DLPack and a from DLPack or something that allows you to just move around. But then beyond that, that we use a lot within Rapids, we also have this cuDF interface. And this might seem familiar in terms of the like other array interfaces that we have in like NumPy world and the way that we do dispatching and accessing within the NumPy community. A library can come along and implement the cuDF interface on their GPU array representation. And if they do that, it means we can just cast directly from one array type to another array type. They will just check, does where you're going have cuDF interface? If so, here's the array data that you need. It will call that method and it will come out the other end of what it needs to be. And it just means that everything gets really cleaned up. And we've already got good adoption within the community. So we've seen Number a bunch. We're going to talk about CuPy in a bit. I've got a little PyTorch example here, although I don't have PyTorch installed in this environment, so don't run all these cells because they won't work. But you can just hand from one of these to the other, and it'll just move around. It won't copy. It'll be really neat. So if you want to do some kind of workflow where you're going to load some data in with CuPy maybe and do some like NumPy style stuff, mush your array around, do bits and pieces, and then you want to switch to PyTorch to do some model training, you can just hand that array over from CuPy to PyTorch and then just get going with your tensor. Yeah, question? Yes, they do. Sorry, purple is DLPack and yellow is cuDF interface. I think the legend got chopped off. So let's have a quick little look at this. So if I use CuPy, which I know we haven't come on to CuPy yet, but if I create a CuPy array, we should see my memory usage increase. Yep. My GPU is busy allocating my CuPy array. My memory usage increased there. I'm going to keep these plots open so you can see a bit more of what's going on. And if I have a look at the type of my CuPy array, this is a CuPy core array, which we'll play with more in a minute. But this is an array. It's on the GPU. And I can just hand that to Number. If I want to do some stuff in Number, I can just do to device, as I've been doing with my NumPy arrays. But if I give it a CuPy array, Number will go like, oh, can I just have your memory addresses and I'll just use your array. So if I create a Number array, nothing changed, right? My memory hasn't increased, nothing has changed. I have one array in memory. I just now have that array in CuPy clothes and Number clothes. And they can each operate on it, and they will each modify that same array. It's basically like having two pointers to one array. It's just that they're different branded pointers, maybe. And then if I wanted to, I could also import PyTorch. I won't in this example, but I could do torch.asTensor and give it one of these things. I have to explicitly say, this is going to be a GPU tensor, because PyTorch will do CPU and GPU. We just say, okay, can you make me a CUDA tensor from this array? And PyTorch will also just create a new pointer to this array. So you can hand around between these things. You can do some steps in one tool. You can do some steps in another tool. This is all part of the goal of as you can see, GPU computing will give you acceleration. It will give you more performance, but it's up to us to come and meet you where you are in terms of the tools that you're using to kind of just make your lives easier. So this is one of those places where we're really investing in interoperability and everything to make your life easier, I suppose. So, yeah, sure. If you got out of memory error, I would either restart all your notebook kernels or stop all your notebook kernels to release all of the memory from pointers, or make the array smaller if that array is too big. That's like an 8 gig array, so I don't know what. If you're on the binder, you should have got 16, but okay. So yeah, let's now head back into code world and have a look at CuPy. We go for about 2 hours, and we're just over halfway through the material. The material is probably going to ramp up and get a bit faster. I might go on a few more tangents, but thank you all for still being awake during your fourth tutorial. on a warm afternoon. So let's talk about CuPy. We're basically going to leave behind all of the horrible new words I introduced, threads and blocks and all those kind of things, and we're going to move up a layer of abstraction to just NumPy. Right? We're going to move up to the NumPy layer. So if I import NumPy and CuPy, I'm also just going to, you'll see me do this a bit. This is basically just so I don't cheat in any of my timings. I'm just telling Python to wait for the GPU to be done, because sometimes CuPy is helpful and like asynchronously dispatches stuff and then carries on. And so I'm harshly telling it, don't be helpful here. Let's actually see what these things do. So if I wanted to in NumPy create a big array of ones, I would do it like this. I would allocate this array of ones. It would take half a second or so to create me an array on the CPU. I can also do exactly the same thing on the GPU, create myself a big array. I've got my little synchronize here just to make sure we're actually timing this accurately. If I run this, it only takes 110 milliseconds to create a big array of ones, because we're using all of the threads in our GPU to just push all of those ones into our memory. So we get some little performance increases just in terms of constructing big empty arrays. We can also do all the same kind of standard NumPy stuff you would expect. So we can multiply our CPU array by 5. We can multiply our GPU array by 5. Just goes a lot faster. Same thing, much faster. This is kind of coming full circle back around from like right at the very beginning. We were comparing bad Python for loops with poorly written GPU code with NumPy. Now we're right up at CuPy, which is just well-written GPU stuff. You're like at that next level of performance. But I think hopefully it's just been interesting to see how GPUs work and how you can write code for it. But also it's useful for you to have all of these concepts in your head that we've introduced so that when magic stuff happens like this for you and stuff just goes really fast, you understand maybe a bit more about what's happening. And when things go wrong, you maybe understand a bit more about digging back out from failure states. So let's also just have a look. Let's take our array and just do some more operations. Let's do a couple of sequential operations. These are operations which, if we did them in our kind of unsophisticated way with number at the beginning, we would be doing lots of memory copying back and forth to the GPU. Right? So if I do this in the CPU, it's going to take 511 milliseconds. If I do this on the CPU, CuPy should do intelligent memory things for us. It shouldn't do any of these unnecessary copies. So I run this, again, this is like less than an order of magnitude faster. No, more than an order of magnitude faster, because it's just done these clever things. And I think you can see the utilization kind of ticks around. We can see what's going on. Now, CuPy has not 100% coverage of the NumPy API, but it's got a good chunk of like the most common stuff. If you run into things that are missing, you can open issues and that kind of thing, but they're very responsive and fleshed it out. Most of the time you'll find what you need. And so it's got like a whole implementation of some linear algebra stuff. You could do like an SVD. If we do that in NumPy, that might take 282 milliseconds. Now, if I do this on the GPU, we might end up waiting a little bit longer the first time we do this. And this is all around setting up that memory, moving that memory around, setting up context, and doing kind of bad things with small amounts of data. But those things are done now. So if I do this again, it should get faster, maybe faster. Maybe it's topped out there. But you can see it's still possible to do things in CuPy that are slower than NumPy. So you kind of got to think about, am I using big arrays? Am I using things that are like hard and slow? If I'm doing stuff that's already fast and performant in NumPy, great, use NumPy. NumPy is awesome. But if you're starting to feel pain around performance, explore CuPy as an option, because on large problems, it will be good at solving them. Yeah, sure. We're at a point where most of the things are equivalent or faster. Some things are just algorithmically not possible to distribute. But yeah, it's kind of just, it's been implemented and it is there, and you should see some gains. Sometimes these gains are done through like intelligent memory management rather than parallelism. But yeah, there's some things like, I come from like weather and climate, where there's lots of things, algorithms that just make no sense to do in parallel. They're hard to put on a supercomputer or an HPC, where you're just kind of stuck in single-threaded land. And not everything's going to be great as well. There's down. I guess we tend to like, if you go on the Rapids website, there's like the graphs of like, this is 10 times faster. This is a million times faster. This is whatever, we've profiled a whole bunch of stuff. Some stuff is in the millions of times faster range, but other stuff is going to be slower. And that's fine to just keep using the CPU for those things. Is there any question? Oh, so I know this is everything you need to do it. I'm just doing this to make the timing accurate. If I took this away, it would probably falsely say that was, oh, maybe not. Sometimes it falsely says things are like faster than they are. But that's literally just there for my showing you stuff, but don't worry too much about that. Yeah, so I've just imported CuPy as CP in the same way you would import NumPy as MP. You can use most of the same stuff. Also, to move on to the next little bit, NumPy can do dispatching to other NumPy-like things. So you can get into a state where you import CuPy, you use CuPy to create your data, and then you just use NumPy like normal, right? And we can do numpy.svd and give it our CuPy array, and NumPy will look at what it's been given and go, that's not a NumPy array, that's a CuPy array. CuPy, you do the thing, and it will dispatch and hand off to CuPy to do the thing, and then the results will come back up. So you can do mp.whatever on a CuPy array, and it will behave exactly the same. So if I just run this little example here, it does the same as doing CP. So this is a bit like with the CUDA array interface, you can pass data structures around. You can also just use CuPy arrays in places where you would normally use NumPy arrays quite a lot of the time, and it will be fine. There are some caveats. I did a bunch of work with the X-ray folks around using CuPy within Dask and within that. And there were places where the tools were doing numpy.asArray and trying to convert the arrays, trying to make sure the arrays were NumPy arrays sometimes. Sometimes that's because you want to pass a scalar in. And it's just like, oh, there should be a NumPy scalar. So it just tries to convert it, and that was clobbering the CuPy array. So there's places where work needs to be done, but often it's totally valid to just try passing a CuPy array, and a lot of the time you'll have success, and sometimes it's just a bit of refactoring to get around errors that are coming up. So the last little bit here is the questions that we had about devices before. So basically everything we've done, we've just let it do its thing. It's put everything on device 0. You've all only got one GPU, so haven't noticed. But with CuPy, and all of these tools, but with CuPy you can say, I want you to create an array on a specific device. So instead of creating it on device 0, can you make me a big array on device 1? It wasn't that big, was it? Still not that big, but you can see I made an array on the other GPU this time by just specifying which device that's on. You can also tie yourself in knots, I guess, with this. If you have memory on different GPUs, you have to think about how does that memory move around. But in a little bit, we'll come on to doing multi-GPU and multi-node, multi-GPU work in a little while. So I've got a very short exercise here for you to just go through CuPy, maybe test your NumPy knowledge a little bit, and just try and do a few operations just to see how familiar it feels doing it in CuPy. So let's give this 5 or 10 minutes. Please use your post-it notes to let me know when you're done or want to move on. I'll wander around if anybody has any questions, so just chuck your hand up. And then we'll move on to cuDF. So this one was reasonably just exercising the API and showing similarities to NumPy. So we can use the A-range to create a big array, as we have done a few times. We can have a look at how big that array is, right? That's like a 4 gig array roughly. We can see how many dimensions it has. We can see the size of the array. We can see the shape of the array. And then we can use standard operations like linspace to calculate that kind of array. So this CuPy can assign these arrays for you directly on the GPU. And these don't have to just be 1s and 0s and whatever I've done before. You can use kind of normal NumPy stuff. You can do random. And you can do all kinds of sorting. This would be like a parallelized sort. You can see the GPU is quite busy doing that sort then. Less busy second time, I guess. And you can do reshaping. So hopefully that's kind of given you a bit of an insight into how using these lower level tools we built up, these APIs that look and feel familiar, right? But they're just leveraging the GPU where they can to make your life easier with more performance. So in that vein, let's move on to cuDF. I'm actually just going to restart all of my kernels because I'm eating up my memory a bit here. But if I import cuDF, cuDF is to pandas as CuPy is to NumPy. So it is this data frame library that is GPU accelerated. Kind of if you dig under the hood, the arrays that make up the data frame are CuPy arrays, and they're kind of built together. So you can use them in conjunction in the same way that you would use pandas and NumPy together. You can use cuDF and CuPy together. So let's kind of have a look at this API and explore some of the ways that it's similar. So if we import pandas, as well as importing cuDF, we can do our read CSV in pandas to load in a small kind of data set here. We can do exactly the same in cuDF, read the CSV in, and you'll get something. Oh, yeah, there's the GPU setting up. There we go. Right, so we get exactly the same looking thing, right? This is a data frame. You look at the head of it, it looks exactly the same. You can see my memory's ticked up again, so this data frame is sat now on my GPU. When I call head, it just grabs the head of the data frame and just moves that back to the CPU. I think it actually does two pandas under the hood and then plops out the nice representation of pandas here. So we can see it's the same kind of thing. We can do all of our normal operations that we could do. We can change the column names, we can drop columns, we can kind of play around with our data frame. We can see it's got over 1 million rows. We can do things like, oh, I want to take, this is like Wikipedia page view data, so there's a column of like which language of Wikipedia it is. We can just count the number of pages that are in English. And these operations are running on the GPU. This should just look like I'm doing some Pandas stuff, but this is just happening on the GPU. I could do a group by. I could group by the language and then do a count on each one of those. If I did that. You can see my GPU utilization. These aren't hugely taxing it because this isn't a hugely big data frame because I want you to be able to run it in Binder. But you can see all of these kind of data frame operations are working and doing the same kind of thing. Now, yeah, let me just catch up to that. Yeah, so we can kind of do our nested accessors and all those kind of things. These arrays behave the same, they have the same interface. But I've already had some questions about what about the core things that might be different here? What about D types? Does it support all of those D types? Does it support all the same kind of things? And it has a good overlap of the API. It covers a lot of standard stuff. It has most of the standard D types that you would expect. I think, I'm not sure if, Charles, do you know, do we have dict types? There was. Yeah, okay, so we can support dictionary types inside data frames. But these are recent, that's a recent addition, I think. And this is kind of ever expanding. And I know that Panda support is expanding in terms of types that it supports, and we're kind of catching up. So everything we've done so far on the GPU has all been around numbers. Right? We've been playing with numbers, we've been playing with arrays. And I think something, if you're kind of in the GPU community, GPUs have a reputation of not handling strings as well, or not having as mature support of strings. And Pandas is a heavily string-based tool, right? A lot of stuff you're going to be doing in data frames is string-based. And so we have another package within Rapids called cuStrings, which is trying to give this high-level string support in GPU world. Because I think it's funny, strings are something you take for granted in Python and other language, but it's something that is non-trivial compared to dealing with numbers. But because we have good, fast string support on the GPU, we can do things like uppercase and lowercase, and all your kind of normal string operations, and those operations are being parallelized on the GPU. So if you're going to go over a column and you're going to uppercase everything, one thread will get a row from that column, and it will just work through an uppercase. And we've got all this stuff written for doing those kind of things. And cuStrings is a really interesting library because we see these things being used in different ways. I remember somebody telling me a story about data formats and how people store data. A really popular way of storing data, sadly, still within the Pandas community is CSV, which is just a fact of life, I guess, is having to use CSV. And one of the challenges around CSV is it is a string-based data format. And when you read in a CSV file, you just have to keep reading until you get to commas and new lines and kind of store stuff. But then you have all of these strings, and you have to do a type inference on every single one of those because there's no type information about what's going on in there. And it turns out GPUs are actually really good at that job because you can just parallelize that. It's a hugely parallelizable problem, is just look at every one of these strings and do a type inference on it. And so reading in data with cuDF from CSV can be really, really fast compared to Pandas because we can hugely parallelize this load. So if you are stuck in a land with CSV, you can use cuDF to get huge reading performance. maybe even use cuDF to write out some Parquet, and then you can switch back to pandas. Like we've had folks come into the Rapids community and just use cuDF really heavily for bulk converting CSV to Parquet and then moving on with their lives. So there's a hand. I mean, yeah, Parquet seems to be like the most popular that we see and get asked about, and like we've driven a lot of support into that. But like we also have like an awk reader and other, we have other format support. Parquet is just the one that we seem to hear about more often and get demand for. Obviously within like the geosciences community, NetCDF, HDF5 like is a popular format. There's like various things, but yeah, Parquet comes up a lot. So the other thing we can do in cuDF is we can do UDFs. So you can write a function and apply it over your data frame. And these functions can be pure Python functions, or they can be the number functions that we played with before, and probably a few other things as well. But we can just use apply to do this. So if we do like a really basic UDF here, if we want to take a number and just do like some filter on it, so say if this number is less than 5, we're just going to round it down to 0 and just chop everything off at that point. We can write a very simple little bit of Python to do that. And then in cuDF, we can do apply here, right? So we're going to take the requests column, number of requests for a page, and we're just going to apply our UDF over it. I should actually print that out afterwards. We can see these all get chopped off because there's like one or whatever things. But when we call this apply, that function is being taken. It's being compiled down through number into a CUDA kernel. All of the configuration around threads and blocks and all of that kind of stuff is being decided for you. It's being executed on the GPU, and the result is being assigned back into the data frame. So this is why we did like a whole bunch of setups. So you can see it's actually really like quite neat. You can write a basic function, you can give it to cuDF, and it will do all this magic that you've been doing manually on your behalf and kind of set things up for you. But also, if you have reason for kind of getting under the hood and wanting to dig down, you can also just write these things directly. If you import a number, you could write your own kernel where maybe you're going to take, you've got in column and out column. These are if we're working on like a series of data in pandas or in cuDF, you'll be given a pointer to the whole column, and you'll be given a pointer to a new column that is kind of created for you in memory space, and that column is going to be replaced at the end. It will swap the pointers around. It's kind of given you the input data, it's set up the output data for you, it's given you pointers to both of those things, it's given you any arguments that you want to happen based in your function call. And then you do your same kind of stuff. You do, get my index, which row do I operate on within this column? And then you do your kind of thing we were doing before. You take some value out of the input, you do something to it, you put it into some place in the output. And we can run that on our data frame using the for all call. So we say for all the things in this column. We're gonna, oh no, it's on the, sorry, wrong way around. It's on the function itself, right? So we have our CUDA kernel. We do CUDA kernel.forAll. So instead of doing our square bracket configure call it, we're saying like for all and then giving it some like data structures that it can operate over. This is like another number feature we've not touched on yet. But we're going to say take for all of the things in the length of the column, we're going to give it our input column, we're going to give it our output column, we're going to multiply it by 10. And we can see we get our new column. So that kind of handles that for you. And then we can also do rolling windows. So if we want to do some kind of view over our table where we want to like roll over it and do some kind of neighborhood operation, we can define a function like this where we say, I'm going to do a neighborhood mean, I'm going to take in a window. This window is going to be an iterable. And we can calculate something. Say, if I want to do a mean, I'm just going to have a counter. I'm going to iterate over the iterables in my window, and I'm going to update that value, and then I'll divide it by the length. And then we can do our column here, right? Our data frame dot requests dot rolling for rolling mean, and we can give it kind of the window size and the start position. I forget what true means here. Let me just remind myself. Center, right? So this is when we roll over the window, who do we update in the output? Do we update the top or the bottom or the center? So we're saying the center here. So we're going to roll over that, and we're going to apply our neighborhood mean. So these are how we can kind of create little functions yourself that you're going to apply over your code, and these will be just in time compiled down to like fast GPU stuff that can then be run for you. So we're doing quite well, chugging through this stuff. We've got 2 more notebooks. Got about an hour and a half left of the session. We've had a few breaks. So let's dive straight into the cuML notebook, and then maybe take like a 10-minute break at the end, and then we'll go through. I'm going to do a bit on like Dask and multi-GPU. So I might spend a chunk of time talking about Dask before we dig into that. But then we should be kind of wrapped up a little bit ahead of time. We have a bit of time left back to go and find some folks for dinner. So let's talk a bit about cuML. cuML is the scikit-learn of this ecosystem. It follows the same API. It implements a lot of stuff that should be familiar if you use scikit-learn. I appreciate this group. There was like fewer hands up for scikit-learn, but let's dig into this anyway. You can do some cool stuff. So when you're working with scikit-learn, it's common to use NumPy and pandas in concert with it, right, to do your data loading and manipulation and all that kind of thing. Same exists in this ecosystem. You would use cuDF to read your data in and pass it to cuML. So if we read in some data here, we have some like health data about some people, and what we're going to do is we're going to try and train a model, a very basic thing, to predict whether or not somebody has diabetes based on some other attributes about their health. So we'll take in some data here. I think this stuff is pulled from some like Kaggle examples. We're going to drop off our outcome column as to whether they have it or not, and we can have a look at that so we can see we've kind of got this binary array of whether this person has diabetes or not. And then we can use kind of standard things that you would expect to see in scikit-learn. So if we want to split our data out into like a training set of data and a testing set, we can use test, train, and split, same as you would in the scikit-learn. We're just importing it from cuML here instead of from scikit-learn. So if we just assign that out, decide we're going to use 20% of our data for doing that, cuDF is going to load the data in, it's going to hand it off to cuML, it will split that out. We'll have a few data frames here for running through. And then we could just train like a neighbors classifier here and do that with cuML. That was like way faster than I expected it to be. Okay, that was really fast to train that one. And then we can do predict on that, give it some data, and we can score. Right? So this is kind of very similar. This is giving us like a 69% accuracy. It's not the best model in the world. But the main point I want to show you here is that it's the same API, it's the same interface. If you're used to using scikit-learn, using cuML should feel very similar. Again, if there's things that you're using that you find don't exist, raise an issue, we're kind of just trying to gather like priority more than anything of like how can we implement all the things that folks want, but we hit the majority of stuff that our users are asking for at the moment. So that was like a very brief overview of cuML. Yes? Well, I mean, I guess like that in that context, we're talking about like machine learning stuff. It's mostly like whacking straight lines through plots of data, kind of level of things which scikit-learn's bread and butter. Whereas it's useful in conjunction with like deep learning as well. But like PyTorch is great. We consider PyTorch to be like part of this ecosystem. We can cast between all of that. It's all. I think that's the thing. Like Rapids is a thing where like it's an NVIDIA initiative, right, to contribute to the data science ecosystem and the PyData ecosystem. But most of the time, we're just contributing to existing open source projects, whether that's contributing code to PyTorch or to CuPy or building our own tools like cuDF, and then just making sure compatibility is there, going and telling people about it, trying to make more performance there. Because at the end of the day, if all of these tools are really good and they're really compelling, then you're all going to go and buy NVIDIA GPUs to use them, and then we're happy, right? That's kind of the plan. So there's got to be a plan. So, okay, that notebook was much faster than I remembered, so I'm just going to dive straight into Dask, and then we can kind of wrap up. So everything we've done so far has been on one GPU. We like touched briefly on how we can like create arrays on other GPUs. But what happens when you are really pushing the GPU hard? You're pushing, you're seeing a big red bar on utilization, and it's just busy doing stuff. Well, I encourage all of you to get to that point before you even start worrying about anything I'm going to mention in this notebook. And it's like a long road to go to being at that point where you are really saturating like a high-end graphics card. But once you do get to that point, you're then going to want to break beyond that. And that is great. You can do that. You can add multiple GPUs into your machine. You can buy multiple machines and cluster them together. You can have a nice big supercomputer with lots of GPUs in. And you can run basically the same kind of code that we've been talking about here across those machines, leveraging all of this hardware together as one in concert. But this is adding a layer of complexity on top. And if you can get gains without doing that, then you should do that first. Right? This is kind of what we talk about this a lot in Dask, whether it's CPU or GPU. Do whatever you can do to squeeze the most performance out of what you've got on a single device, single machine, whatever, before you start worrying about distributed computing, because things do just get more complex. But eventually, if you've got big enough data and big enough problems, you'll get to this point where you'll need this. And this is where Dask comes in. So apologies if you came to the Dask tutorial, you know what Dask is, but let's kind of do a bit of an overview of Dask. Dask is a Python library for scaling out your Python code. The way that it effectively works is it decorates Python. You can decorate Python functions, or you can use the built-in collections to lazily compute code. It lazily executes your Python functions, and it does this by building up a task graph that describes what the computation would look like if you did it. So you can build up like a series of function calls. Those function calls have inputs and outputs. And then when you get to a point where you say, okay, I want this to happen, that graph will be passed to a scheduler. The scheduler will pass tasks to different workers. Those workers will do the thing, and then it'll all get combined back together into a result. And so this is really powerful if you have a laptop with more than one CPU core. Maybe you're not using NumPy or something that's already got multi-core capability. You can really just leverage your local hardware by using Dask to like scale out your Python calls in a distributed way. But then also, your code doesn't need to change if you want to add another machine and another machine and then move to the cloud and get some VMs and get bigger VMs. Like everything stays the same, you just make your cluster bigger. You have to start worrying about how those things talk to each other, but the code stays the same. So as just like a very small example here, I'm going to create a distributed Dask cluster. This is my little cluster object. This is just going to fill my machine with Dask, basically using local cluster. It tries to do things intelligently here. So on my machine, it's created 4 workers with 12 threads. This is smaller than I'd expected. Okay. Anyway, it's created 4 workers with 12 threads and nearly 100 gig of RAM, because that's what's in my machine, and I can see my workers here. It's just decided how to carve up the CPU and stuff. Now, once I've got this cluster, having this client object existing in my global scope is enough to tell anything that Dask does to use this cluster. But also we can interact with that client directly. So at like its most lowest level, we could just say, Dask client, can you please just send this function call off to some worker to calculate this for me using the futures API. So we can just do 10 plus 1. That's executed on a Dask worker for me. Or I can use the high-level collections. I could use Dask array, which looks and feels like NumPy, and we could create a big random array with 1,000 elements in. We have to chunk this array up in order for Dask to be able to distribute it. It's going to like put pieces of this array on different workers. Those are just NumPy arrays, but it's going to put all these little bits of array around. And then when you do your operation on it, like taking a mean, it will do like a mean on each chunk, and then aggregate the results together and do a mean on those to get your overall answer. Right? So it's kind of breaking your work down into little pieces. A lot of work has gone into these collections to try and make them as performant as possible. You notice there's like a parallel here in what I'm talking about. Like you've got GPU acceleration with things that look familiar, and then you've got Dask distributed acceleration that looks like things that are familiar. And what we're kind of building up to is like you can smush those things together, so you then get really fast hardware and lots of it to do distributed computation. So if I just run this array example, I have to explicitly tell Dask to compute this thing, because Dask tries to be as lazy as possible. It tries to not do any work if it can help it. It'll only do things if you actually say, no, I need the answer to this before I can move on here. So you have to call .compute. We can see we've done this operation. This is run on Dask. Now, that was like a very, very high level overview. Right? But hopefully you've got the concept that we have high level collections. We have this distributed API that lets you kind of chunk your work up. And then to get that, to get these clusters, you need to actually start the Dask processes. Now, when I did this before in this little bit of code here, I let Dask do its like auto config thing. I didn't give it any configuration. It just had to look at my machine and made some stuff. What this basically does under the hood is it starts a Dask scheduler. You can run this on the command line if you just do Dask scheduler, and it starts a Dask worker and points it to that scheduler. The auto inspect like made a few of those just based on my machine. But we can do that in like lots of different ways in lots of different places. As long as you've got somewhere with a Python environment that matches the one that you're working in, that has Dask installed, you can just like SSH in or submit jobs or whatever, HPC, cloud, it doesn't really matter where you are. As long as you can run a command, you can like pull a Dask cluster together. But that's not very fun, really. So we also have these cluster managers, like local cluster, which we've seen already, that tries to wrap that up for you. Right? So we can, from Dask distributed, we can import local cluster, and we can say, make me a local cluster, which is what the auto config did. But we can make this cluster automatically. And we also have like a whole bunch of other cluster managers. So if you have a Kubernetes cluster, we have kubecluster. If you have a Hadoop cluster, we have Yarn cluster. If you have various HPC systems, we have like SGE cluster and Slurm cluster and all these kind of cluster managers that are just aware of the hardware they can run on. If you're using the cloud, we can like spin up VMs to start the processes on. If you've got containerized platforms, we can start containers. It doesn't really matter where your stuff is, you can run Dask there. A like super popular one that we see come up a bunch is SSH cluster, which just SSHs to other machines and starts Dask processes on them and connects them back to where you are. It's great if your colleagues have got desktops or workstations that they're not using enough. You can just steal those by SSHing to them and then strapping them all together into a little ad hoc supercomputer. It's great. It's really helpful for doing these kind of things. But by default, Dask is kind of staying within the PyData ecosystem, right? It's NumPy, it's Pandas, it's scikit-learn, it's these kind of core libraries. And so if we want to do GPU stuff, we have to give Dask a little bit of knowledge about GPUs. And we can do that ourselves, right? We could start with Dask workers and tell them about the environment. We could set config. We could do all sorts of things. But again, that's not particularly fun because there's like a few things we need to consider. One is that each Dask worker should have exactly one GPU. And so as functions get submitted, they shouldn't be having to worry about distributed GPU stuff. They should be doing the kind of automatic things you were doing where whatever we're doing happens on GPU 0. If I've got 8 GPUs in my machine, there should be 8 workers, and each one should just be able to see one, and it should think of it as GPU 0. And it's trying to do the like less complex version of things, and we're just kind of aggregating those. So we need to start a few workers. We need to tell them, you have this GPU. We actually like mask out the rest of them and say, ignore these. This one is GPU 0 now. We also need to tell a bit about memory management and how things are configured. And you can do that by hand, but if you don't want to, we have another package called Dask CUDA that lives in the Rapids ecosystem, which just gives you more cluster managers and more tools to start things up. The two main things that you'll see is local CUDA cluster. This behaves a lot like local cluster that I showed you that inspected my CPU and started some workers. But instead, that's going to inspect my GPUs and start some workers. So I have 2 GPUs in my machine, so this has started me 2 Dask workers. And it has done all of the configuration. Each worker thinks there's only one, and they're on a different one. There's also another command called Dask CUDA worker. So to replace Dask worker, if you start things up in a more manual way, or you want to start things up by using any of the existing cluster managers, like kubecluster or whatever, you can just say to it, or you should run Dask CUDA worker instead of Dask worker to do the like auto-detective hardware and start like sub-workers on GPUs. And we can connect a client to that. And then we can carry on as normal, right? We have this nice Dask cluster. It has GPUs now. I have these 2 GPUs in my Dask cluster, and I can tell it to do stuff. So in a very basic way, I could say, here's a number kernel. This is a very unsophisticated one. It's just going to count forever and not do anything. But I can just say to Dask, look, submit my kernel. This call is the same as our number call before. We're doing the config bit. We're saying how big the shape and size of that number kernel is. We're not actually invoking it because we're going to let Dask do that later. We're just saying, here's the number kernel. Can you do that for me? And it will send that off. Maybe you saw my GPU flicker a little bit there. And that has finished. So we've kind of taken some GPU stuff, we've handed it to Dask, Dask's done the thing, it's given us the answer back. So that's great. That's a great way of kind of dispatching what we've done already onto remote machines. But then we can also start mixing our collections together. So in Dask, we have Dask array that pretends to be NumPy. In Rapids and GPU ecosystems, we have CuPy that pretends to be NumPy. But what if we told Dask, your unit inside is not NumPy anymore, it's CuPy. Can you do your high-level Dask thing, but just use CuPy as the like smaller arrays? Or the same with pandas, right? Dask data frame. Don't use pandas, use cuDF as your internal representation. And again, you can do that. You can definitely do that. You can tell Dask what to do. There is a bit of setup and config that you have to do to make that happen. So to make your life a little bit easier, if you install cuDF, you also get this Dask cuDF package that you can install, which is basically just all the data readers from cuDF that have been pre-configured to do the Dask thing. So instead of getting back a cuDF data frame, you get back a Dask cuDF data frame. So we have a look at that. We could create ourselves an array. I'm just using from delayed and a little noddy function. This is basically going to create us a big array here, a big data frame with many pieces in it. It's going to have 30 partitions. It's a big Dask data frame chunked out, 30 partitions. Each of those partitions is the demo time series from cuDF, if you want to play with that. So we've got kind of made up this big aggregate thing now. But we just have one data frame, right? We have this GDDF object. This is a GPU distributed data frame. It's got all these bits of data. They're sitting on GPUs in memory. These partitions are probably evenly spaced across the GPUs. They're quite small, so you can't really see them on this size here. But then we can operate on this data frame like we would with any other data frame. We can call head on this, and Dask will go to the first partition and say, can you call head? That is a cuDF partition, so it will call the cuDF head, pass that to Dask. Dask will pass that back to us. It kind of looks magic, and we just get the head of our big data frame back. We could also do a length on our overall data frame. This again, Dask will say to each partition, can you do a length? And then I'll aggregate those for you. If we do a length on here, we should maybe see both of my GPUs are doing stuff now. Right? These chunks of this overall data frame are shared between my two GPUs. They're each going to do stuff. This is how we can start breaking beyond. And then we could do a group by or some kind of more interesting operation just to make the GPUs busy and to show I've got 2 here. If I had 8 here, 8 would be flickering. If I scaled up my cluster to multiple nodes, I could have hundreds of GPUs with chunks of my data frame spread across them, and then do a big operation that's going to leverage all of those. So that's great, that's fun. But the downsides to doing this is these workers, these Dask workers, when they're doing things, everything I've done here so far is like a reduce, right? So each partition is going to do a thing, it's going to get an answer, it's going to tree those up, do the thing again to those, and then give me the result. But what about operations where, well, I need from here to speak to here, and I need this to speak to this, and you're going to have communication going on within your data frames. The group by is an example of one that would have happened. Now, Dask uses TCP for all of its communication. It listens on a port. The scheduler and workers talk to each other over this layer. And when a worker wants some data from another worker, it just opens this connection via the TCP port, pulls the data across. That's great. It works. We've just seen it work. But that's quite in CPU land, that's fine. But when you're using accelerated hardware, you're leaving so much performance on the table, right? Because you're having to go all the way through the network stack to get there. Say I've got the 2 GPUs in my workstation at home. I've got my motherboard with 2 GPUs plugged in. They're on the same PCI bus plugged into the CPU, but for one to talk to the other, it's going to talk up to the CPU, into the Linux kernel, into the network stack, to figure out what's the IP address and where am I going, and it's going to go, oh, it's here. You're going to come back out. It's going to pop back down the PCI bus into the other GPU. Right? It's a very big round-trippy kind of way of doing things. It works, but we can do better. So in order to kind of resolve that, we have nice hardware features, right? They're on the same PCI bus. There is a PCI switch. I don't know a huge amount about PCI, right? But it's a bit like a network. They can talk to each other on that bus. They could just talk directly via PCI. I've also got the little NVLink bridge clip thing plugged into the top of my GPU so that they can do NVLink direct communication between each other. That's another protocol that's on the table that they could use if they knew about this. And then maybe you're in a data center where you've got many servers with these GPUs in. They might have InfiniBand network cards connected over some fancy network in a supercomputer. That kind of network communication can also completely avoid the CPU. Right? The GPU can talk to the network card, it can pop out to the switch, back into another machine through the network card, straight over PCI into the GPU. The CPU doesn't even need to know they're talking. These kind of communications can happen, and they do happen. They're very common in the HPC community. But we can do this here as well using UCX. So UCX is an alternative network protocol that we also support in Dask that basically has a look at your hardware topology between your Dask workers in this context. And it says, right, TCP is here, it's fine, we can talk via TCP, but can we do better? Can we upgrade this connection? So it will upgrade to PCI Express. It will upgrade to InfiniBand. It will upgrade to NVLink. And so, you might be in a setup where I've got 16 GPUs, 8 in each server. I've got 2 servers, right? So these GPUs can talk to each other really fast on NVLink, and in the between server, they can talk really fast on InfiniBand. And UCX will just kind of figure all that out. So if you just set your Dask protocol to use UCX instead of TCP, which is just like a flag that you set, you have to install UCX, and then you set a flag when you create your cluster, this network upgrading will just start happening automatically. So that's like a really neat way where we can just get so much more speed out of this, and it's something that like you just can't do in the CPU world at the moment. Dask also has support for like other network protocols if you are interested. But like this one is like a great one for performance. Other ones are maybe more targeted at flexibility. I know on some HPC systems or cloud platforms, you can't expose like a TCP port, and it's kind of hard to get access to the scheduler, but you can like proxy your Jupyter notebook or something through like a web proxy. We do actually support WebSockets so that you can use Dask through the like Jupyter proxy thing, which is useful. So by default, you get TCP, but you can use other protocols like UCX and WebSockets. I did see a hand. Yes. Yeah, so I'm trying to think if I have a good answer for this. There's a really good blog post on the Dask blog about like choosing chunk sizes, but it's kind of in the context of CPU chunk size selection. I don't have like an easy answer, I guess, for that, other than I'll make a note that we should probably write a blog post about this and get somebody who knows more than I do to communicate that, because it's a good question. Cool. Right. The last little bit that I want to do, which is probably going to take 5 more minutes, and then I'll give you a bit of time back, an hour back, I guess. So we're just coming up to the 3-hour mark. So again, thank you for being awake. It's a warm afternoon. What we've discussed here so far is like, how can I go from doing CPU Dask to GPU Dask, which is great, and we can do all of that. But what happens when you're like, well, I've got one GPU or something, and I want to like mix it in. I want to just dip my toes into like, I'm going to do a big Dask calculation, but I want to see if I can speed up this step, this task, this bit of stuff. Can I rewrite this in number? Can I use CuPy here and just do a bit of it? We also support like resource annotations in Dask. So you basically say, when this function is called by Dask, it should be run on a worker that can supply these resources. And so that it's like an arbitrary thing. Like in this example, I've got like, I'm going to set the resources of my Dask CUDA worker to 2. This is on my workstation. I have 2 GPUs. So I'm going to tell the Dask scheduler, this worker has got 2 GPUs, so you should use those if you get any GPU tasks. But this uppercase GPU, uppercase GPU here, this is just like an arbitrary word, and this is an integer. This could also be like memory or cats or like whatever number you want to measure for this machine. But Dask will just make sure that if I've got a GPU, if I've got a machine that's got this annotation of, I've got these 2 things, and then somebody writes some code where I'm saying, okay, I want to annotate everything in here to say, these tasks need 1 GPU before we submit them, then the Dask scheduler will just make sure that those tasks land on a worker with those resources. So you can then create these kind of hyperclusters. One of the places that I found this to be particularly compelling is when I'm loading data in from cloud storage or somewhere like S3. Making a connection to S3 and pulling data from it is very, very slow. When we're talking about like GPU scale, like performance and stuff, like you have to go through HTTP and TCP and TLS, you have to do encryption and like all sorts of stuff to like get a data stream out of S3, compared to just like reading bytes from like an NVIDIA hard drive or something. And so it's really common in that space. It's slow relative to that stuff, but it's like infinitely parallelizable. And so you can get incredible throughputs from a storage medium like S3 by just distributing data loading. So if you just have like 1,000 Dask workers hoovering data out of S3, you can get really, really amazing throughput. And so that is one of those situations. If I'm reading data from S3, I want lots of Dask workers, basically, is the point I'm trying to get to. But if I'm doing maths or computation, I want GPU workers. And so in my workstation at home, I've got 2 GPUs and however many CPU cores. And if I do CPU Dask, reading in from S3, it will use all of my CPU cores to do my data read in parallel. And then it will use my CPU cores to do the operation that I'm trying to do. And I've tried recently, like, can I switch over to the GPU version and time it and see how it goes? So I was just doing like a mean of some X-ray data set, reading in some ZAR thing from S3. And when I switched over to the GPU one, I only ended up with 2 workers because I've only got 2 GPUs, which meant that that data read slowed down massively because I'm only making 2 connections for S3. And so doing my timings, my calculation, my mean that I was doing, sped up by an order of magnitude, but my data reading slowed down by an order of magnitude. And so I ended up kind of roughly where I started, and it wasn't that much better. But then I could try starting a hybrid cluster where I have CPU workers utilizing all of my CPU cores and GPU workers using my GPUs. And then I can just use annotations to say, right, CPU workers pull the data in from S3 and then move that to the GPU. GPU workers, you do the mean and then give me the result back. And that allowed me to get like the best of both worlds, right? I've got this nice parallelism using all my CPU cores, and then I've got this accelerated computation using the GPU. This is where resource annotations come in. This is like a less mature part of the space that we're like actively working on to make this smoother, but it does work today. So that's pretty much brings us back full circle to the beginning. Thank you all for still being here, I guess. Hopefully this has been interesting to you in terms of actually running some code on the GPU, getting to grips with what these things are. I've introduced some new words. You may be thinking, I never want to hear those words again, but like it's an interesting space that's like under active development. There's a lot going on here. There's still a lot of work to do. But please, I encourage you to like try out these tools. If you have GPUs, go and see how they fit into your workloads, raise issues, get in touch with us. There should be links around in places, but like the main place to come through to us is our website is rapis.ai, which has links to our GitHub and Twitter, and we have like a Slack that you can come and join and like just come and speak to us about what's going on. We primarily focus on data science type workloads, but like most of what we're doing is just broadly within the PyData ecosystem. So we've touched on all sorts of spaces here. Don't be put off by data science if you don't like necessarily see yourself as a data scientist. If you're a Pandas user or a CuPy, a NumPy user, or any of those kind of folks, like this kind of stuff should hopefully help you. So with that, I will say thank you very much. And yeah, I'll stick around for questions if anybody has anything they want to ask or chat about. So. I'm going to turn off that binder cluster in like half an hour. So if you want to save any of those notebooks, I mean, they're all on GitHub, but if you've made changes and you want